And we will move to the last talk of the day. And this is by, I would say, the grandfather of the Snark, maybe, Brian Butterworth. Brian has been the animator year after year of several European networks that have drawn us together. And I suspect I should have mentioned you, Brian, this morning when I showed the kink in the curve. I think you're responsible for the kink in the curve and the surge of interest for numbers and the Snark Effect with all of this European money that you drew into our labs and getting together in interesting places. So thank you for all of those years. And you're going to talk about space, time, and number in Dyscalculie.
Well, thank you very much for inviting me. I've made one or two contributions to the 967 references to Snark, but I've only ever written one paper on Snark, which I'll talk about a bit later. So I think it's not working at all, is it? That's okay. I mean, Stan, of course, is the godfather of Snark, and I think it was absolutely brilliant science to spot this particular phenomenon. I think it's also quite interesting that Stan has left it to the rest of us to carry on that tradition rather than doing a great deal in it himself. Let me start by a quote from Stan from the A&P Ticks volume. He says, "The metaphor of the number line summarizes this wealth of association and interrelations between number, space, and time. Yet it must be recognized this is only a figure of speech and will ultimately have to be replaced by a detailed understanding of the underlying brain mechanisms." Then there's a quote here from Wim Fierce and colleagues, and who says that this close resemblance in the performance of both tasks, number and space, has led to the conclusion that the mental number line is more than a metaphor, and that its representational format is functionally isomorphic to that of physical lines. Now, he's not, of course, attributing this to himself and his colleagues, but to others who make what would be a simple logical error, that because two things are similar, they must be the same. And then what I say is space is a handy model for many cognitive dimensions. And I'm now just going to expand on that very briefly by taking a non-numerical area and showing that it gets mapped onto space in a very similar way to numbers. And that's music, or pitch. Let's be more specific, it's pitch. And we call this the spatial musical association of response codes. And we're thinking about the representation of pitch in space. And we're looking at it low to high and left to right, using a very simple stimulus-response compatibility paradigm, rather like the Simon effect. And we have two manipulations in this particular study. One is an explicit manipulation where the judge has to say whether the test tone is higher than the reference tone, and there's an implicit task where the subject has to judge whether the tone comes from a percussion instrument or a wind instrument. And we had two groups just to look at the effects of experience, musicians and non-musicians. So this is what it looked like in this particular study. We actually mapped high and low onto near and far. And these are the stimuli. We had C4 as the reference stimulus, and then we had some tones below and above it. So we had a compatible condition here, where that's high and that's low, and an incompatible condition where you have to press this key if it's higher than the reference tone, and that's where it's lower than the reference tone. And we just had ordinary binaural headphones on. Okay. Then for the explicit condition, you had to press a left key if it was low and a right key if it was high. And here you had to press a left key if it was high and a right key if it was low. And so if we look at performance with musicians, you can see that you get a nice high to low effect in non-musicians, and a nice left to right effect in also in non-musicians. But this is for the explicit task, but in the implicit task, you find that there's no Snark effect, where you just have to decide whether it's high wind or percussion in the non-musicians, but in the this is left to right. But in the musicians, you do get a Snark effect, both high and low and left to right. So there's something about musical training which encourages musicians to hear for the pitch, even though they're not actually being asked to do that in the task. So I just give this as an example of another dimension in which you get spatial mapping for some reason or other. We can, if you're interested, discuss that later. So I'm not really going to discuss what Stan thinks I'm going to discuss and what's on the program. I'm really going to, since I'm the last speaker today, I'm going to just offer some general reflections, and I'll talk a bit about the relationship between spatial tasks and arithmetic right at the end. So I've got some general reflections here. So, for example, is numerical magnitude always represented in the same way, or are there different representations of numerical magnitude? Are there triple codes, maybe even quadruple codes? So we know that there are measures, continuous magnitudes, which are uncountable. There are cardinal numbers which are countable. There are ordinal numbers which are countable. They're well ordered, just like cardinals. There are also categorical magnitudes, which Wim mentioned earlier on, so you can categorize numbers as large and small, or large, middle and small, and so on. And there may be several different spatial scales as well. So if you're looking at, for example, some kind of metric isomorphism or homomorphism between number magnitudes and some spatial scale, which spatial scale are you looking at? Second question I want to address is, does the so-called mental number line have an intrinsic directionality? And then something that Wim addressed earlier on is the subjective scale of numerical magnitudes independent of the task you're using to explore it. And then I'm going to talk a bit about how not to measure the subjective scale, and which has been touched upon briefly earlier on. And is a subjective scale of numerical magnitudes the same as the subjective scale of space? And I'm going to say, I've got one experiment I want to report on that. And then I'm going to say something which was down in the program about doing spatial tasks and doing arithmetic. Okay, so intrinsic spatial directionality. A lot of people think that the mental number line, or some metaphor of the mental number line, has intrinsic directionality. If that's the case, then left to right tasks should be easier than right to left tasks. Let me show you two tasks that we published last year, year before. The line marking task, which you've heard before. Here we manipulate the start points and the end points of the number line to get people out of their familiar habits. Also, of course, we wanted to explore the subjective scale. Is it logarithmic or is it linear? So obviously, if you put the start point with quite a high number, then you should be farther up a logarithmic scale. You should behave differently than if you put the start point lower down. And we did it left to right and right to left. And we also had a line construction task, which people like Gallisto are really keen on. Indeed, so are we. Because here you have to do some manipulation of two samples of the line, and doing this manipulation should give you a better idea of the scale of the line. And here you're given a sample, 12 to 23 in this, the top there, and you have to construct the line, extend it out to 45, and you have to do it from right to left. So if there's an intrinsic directionality, there should be some advantage in the left to right conditions in both of these tasks and in the right to left condition. So this is the data. And as you can see, the lines are completely overlapping. The midpoints are completely identical, and the y value of the curve is the same for both left to right and right to left. That's in line marking, and here we have it in line construction, showing these should have been labeled. So again, you get absolutely no difference at all between the two tasks, both in the mean and in the slope. And as you can see, there's absolutely no logarithmic component to the task. So that's one piece of evidence that there isn't intrinsic directionality. Now, it's true this wasn't a timed task. I mean, people could take their time in making the response, so it may be that there would be a time difference as time cost to going right to left. We don't know, but certainly not. There's certainly no difference in the accuracy, which is what you might expect. Now, of course, there are explicit mental number lines that about 10% of the population have. These were described by Galton as number forms. This is when thinking about a number or seeing a number automatically evokes a particular spatial representation of the numbers that you know. They come in many different shapes and sizes. Here are a few from a study we did a few years ago. I'm not going to go through them, but you can see there, none of them are linear. None of them go simply from left to right. And in fact, if you count the proportion of subjects who had number forms, which they were willing to draw out for us, we can look at the overall direction. Overall, even though these forms wiggle around a lot, about half have left to right, a few have right to left, quite a few have bottom to top, but none have top to bottom. So nobody thinks that 1 is up here and 20 is down there. And there are quite a lot of other types of number form, some that go behind, some that go in front. So let's just go different tasks, the same spatial scale. Just going back to those two tasks I showed you before, line marking and line construction, and look at, this is bias in, if you like, the marginal error in these tasks. In the line marking task, the thing that really matters is where you start. Okay. So here you've got a significant slope. So as you start at a higher number, so you get a bigger deviation and actually a bigger overestimation. But the length of the, from the start of the line to where the end is doesn't make any difference at all. By contrast, in the line construction task, where you start makes no difference, but the length of the line that you construct does. So these are the midpoints, and so as the line you have to construct gets longer, the midpoint of it goes down. That means that you're overestimating. So the bias in these, that is the scale that you're using, is different in these two rather similar tasks. Let me look at the scale in a different way. This is looking at essentially what I'm going to show is categorical numerical representations versus continuous spatial representations. And this is a study carried out by my student Slava Karolis, whose paper's coming out shortly. So you'll know Titchener's circles, and he has two versions of this task, where what you have to do is you have to open your fingers, make an aperture in your fingers according to the size of the center circle. And either you have your eyes closed or your eyes open, so open loop and closed loop, where you can monitor what you're doing. And as you can see, this is when the outer circles are, so these, where the outer circles are larger, this is the aperture, and this is when the outer circles are smaller, and you can see that people's aperture is influenced, the physical aperture is continuously influenced by the perceptual illusion. Okay, so what happens if you put a number in the center circle. Okay, here are the numbers 1, 3, 7, and 9. What you can see is that the aperture difference in millimeters from a baseline is not affected by, or is affected in the same way by 1, 3, and 7, but quite differently by 9. So there isn't a continuous relationship between number magnitude and the aperture that's being created by the fingers here. So there's a very different spatial scale. There are very different scales for space, which is finger aperture, and number, because that's how they interact. Okay, so one of the questions that comes up is there a dimensional interaction or a task-dependent interaction between number and space? Because there are lots and lots of number-space interaction tasks. And I just want to show you my one Snark experiment here. I mean, we've done a lot of number-space interaction experiments more generally. For example, in number-stroop tasks, you can do FM. We've done fMRI on that, and you find interactions not in the parietal lobe, that is where you've got a number-stroop interference. You don't find the conflict in the parietal lobe. You find it in the inferior frontal gyrus, and if you make an error, in the anterior cingulate. But let me show you another experiment. So here I'm asking more directly, is the neural locus for Snark in the IPS? So there have been several discussions today, and there's Simone Cutini and Marco Zorzi's very interesting NEAR study, which suggests it is, but we might talk about that in contrast to our own in a moment. Or is it in the visual working memory area, which is an area that was suggested by Wim, at least for magnitude tasks, in his talk earlier on today. And here we're going to offer a very direct test, which is TMS. So what we do is we zap a couple of areas in the brain and see if it affects the Snark effect. Okay, and this is the paradigm. So you have a number, and you have to say whether the number is odd or even, or whether it's bigger or larger than 5. So that's the magnitude task. And we zap the frontal eye fields on the right or the inferior frontal gyrus on the right compared to a control stimulation of the vertex. So will any of these affect the Snark effect? Because if the Snark effect is something which is essentially task-dependent, something that's set up in the frontal lobes, then you might expect it to disappear. And the frontal eye fields, well, what happens if you zap the frontal eye fields? Okay, this is a published study, so it should not be new. So this is the classical Snark effect in the vertex. If you stimulate the right frontal eye field, you get rid of the left-hand part, but only in the magnitude task, you get rid of the left-hand portion of the Snark effect. That is, you don't get any advantage for the left hand over the right. And if you do TMS over the right inferior frontal gyrus, you get rid of it altogether, but not for the parity task. So this is very consistent with what Wim was saying about the difference between, say, verbal working memory and visual working memory in parity and magnitude judgments. So it's consistent with a spatial working memory explanation. Okay, so how not to measure the subjective scale of numerical magnitude? Okay, so this is the general theory that many people have been talking about today, is that the subjective scale is directly represented in a line marking task, and that this is like a standard example of how the subjective scale is meant to change as a result of education, from second graders having a logarithmic scale to fourth grade as having a linear scale. And so this is, for example, what Opfer and Siegler say. There's a shift from reliance on from immature to mature representations of numerical magnitude. But can you deduce from these sorts of data to what the subjective scale is like? Well, one of the things that Véronique Izard and Stan suggested a few years ago is that there might be an intermediate representation. Of course, there is at least one intermediate type of representation between the subjective scale and line marking, which is response generation. They have a rather complicated theory, but there's a simpler theory, which is that as you learn an equal interval response grid, you know that 50 is halfway between 0 and 100. You know that 5 is halfway between 1 and 10, and so on. This can inform your response generation, and that would lead to linear line marking. So, and it may be that your subjective scale isn't changing at all as a result of all this stuff, all this learning. It's still logarithmic, but the responses are linearized because you know that's what the task demands. So a subjective scale can appear linear without an actual change in the subjective scale. And of course, it might be true the other way around as well. So, of course, you find that there is a correlation between the linearity of the subjective scale and mathematical attainment, and that's perfectly well explained by this stage here in going from a subjective scale to linear line marking. That is, that the more you know about cardinal numbers or the counting numbers, the more likely you are to make a linear response in this sort of task, and so you'll get the correlation. Of course, it may be that an equal interval response grid is not necessary to linearize a large subjective scale. So let's think about some non-linearized numbers that aren't countable. Okay, non-countable numbers. For example, fractions and decimals. So this is a study we published a couple of years ago. So what you have to do is you have to mark a fraction on a number line like that, or a decimal. This is adults. This is adults' fractions, adults on decimals. This is children's fractions, children's decimals. These are 9-year-olds. And if you can read this, I'm sorry, somewhere where y is somewhere around about 1, you're pretty accurate. Where the r squared is pretty high, above 0.8 or 0.9, that is also pretty accurate. And both adults and children can do these non-countable numbers in a linear way quite well. So that can't be explained in terms of acquiring a counting scheme, but it can be explained in terms of acquiring better mathematical knowledge. So let me just finish by talking a little bit about number space and arithmetic, because I think what's important about numbers is that you can do calculations with them. So is good number space performance related to arithmetical competence? So here's some unpublished data from Teresa Ucchilano. So we've got 9 and 10-year-olds who've got normal or low numeracy defined as being pretty low numeracy. This is when they're line marking with integers. This is when they're line marking with decimals. Low numeracy kids do pretty well the same as normally achieving kids. So here you're getting a slope of almost one, very high R squares for both of these. There's not much variance. So here are kids who are really bad at arithmetic, but their ability to mark a line is pretty good. Here's another experiment from Marinella Cappelletti and colleagues, forthcoming paper. So here what you have to do is you have a fixation, and then there's a prime. We won't go into what sorts of primes there might be, because they've used this experiment in several different ways. You see two lines, and you have to, for example, say whether the test is longer or shorter than the reference. You make a response. You also do it for time. You can say, does the test line last longer or less long than the reference? So if there's a relationship between your ability to do these sorts of tasks and your mathematical ability, then you should get a correlation. And what do you get? You get, this is better performance, and this is better performance on this task, and this is normalized, and this is better performance on numerical competence on a set of arithmetical problems, and you can see there's no relationship between the two. So let me end with a couple of implications. One is that we like to model numbers spatially, but maybe it's not part of the intrinsic property of numbers, and perhaps the snark is a boojum after all. Thank you very much.